to start lesson 4.4, which is on concavity and points of inflection, otherwise known as inflection points. So the best way to explain concavity is by taking, for example, glass from your cupboard, you put on a countertop and you try and pour something into it, water, juice, beer, whatever you want. If you can actually pour the fluid inside a glass, it's going to be concavity upwards. If you were to turn the glass upside down and try and pour some fluid into it, the fluid would just roll off the sides, and that'll be considered to be concave down. So concavity, for in terms of a graph, the graph of the function has concavity upward if the graph lies above all the tangents. So if you look at all the tangent lines, you can see that the graph's above all the tangent lines. The tangents rotate counterclockwise. Counterclockwise is this way. All right. Slope of the tangent lines increases, and you got to be careful with the increases, right? If you think of a big negative going to a smaller negative, going to zero, going up to a positive value, and getting bigger as we go along. And then f prime of x increases, or f double prime of x is greater than zero. The opposite will be said when it's concave down. All right, so the graph will all be below the tangents, goes clockwise, the decreases, and we have the opposite in terms of derivative. Let's try some examples to see if we can understand what concavity actually looks like. So in the first example, it says find the intervals on which the graph given below is concave up or down. So I have all these little nodes, A, B, C, D, and E. So what I'm going to do is I'm going to create a little concave up on one side, and I do concave down on the other. I'm going to start from the smallest x value, which looks like -8, all the way over to +8. So for the first part, from -8 to A, right, -8 to A, that looks like part of an upside down glass, so only half of it. You could actually extend it to actually see what it would look like, all right? So that looks like it's concave down. We're not sure what's happened to -8, so we're going to put it as -8 and -5. All right, we're not sure what's happening there. Keep on going down for all we know, or whatever the case is. The next one is going to be from -5 to our next point. Looks like a point of inflection at B. So that looks like it's concave up. Once again, you can draw the other half of the graph. You can actually see the shape. So that's concave up between -5 and B is at -3. And then from B to C, we can actually clearly see that the shape is all the way down, right? So that's going to be from -3, concave down, -3, all the way to 0. And then from 0 to x equals 3, it looks like it's concave up, so it's going to be from 0 to 3. And then from 3 up to point E, it looks like it's still concave up, so it's going to be 3 to 6. It's going to be concave up. And then the last one is going to be from point E to the end. Again, I'm not sure what's happening at 8, so we're going to assume that 8's not included. I'm going to say from 6 to 8. Now, the only thing we have to worry about here is here at point D. Some people want to say that's concave up all the way between 0 to 6. We can't say that because there's actually kind of like a little imaginary break in there. We have a test from concavity. So in this case here, it says let f be a function twice differentiable, i.e. take the second derivative. If f double prime is greater than 0 exists over a value of a and b, then we can say that the graph is going to be concave up. If we do the second one, the opposite is going to be true. So when we have x double prime is less than 0 for a and b, then it's going to be concave down. Example number 3 says if f double prime of x equal to 0 for all of a and b, then the graph has no concavity over A and B, i.e. it's going to be just a straight line. Let's do an example. See if we can start connecting some of the concepts. So find the intervals of concavity for the function f of x where x to the exponent 4 minus 2x to the exponent 3. So the very first thing I'm going to do is I'm going to find my x-intercepts. Hopefully it's easy. And what I'm going to do is I'm going to factor out my biggest factor, which in this case is the x squared. So we know that f of x is equal to 0 when we have x is equal to 0 or x is equal to 2. So those are my two x-intercepts. I'm going to find my critical points. And my critical points is when I actually find my derivative. So I'll write the function first. And be taking the derivative of f prime of x is equal to 4x to the exponent 3 minus 6x squared. Once again, I'm going to factor out something if I can. I could factor out 2x squared, so I'm left with 2x minus 3. And we know that f prime of x is equal to 0 when we have 0 is equal to 2x squared, 2x minus 3, which means that this is going to be x equals 0 and x is equal to 3 over 2. Excuse me. It looks like I'm going quickly through this because I think this is all mechanical. Everyone should be okay in this, right? For the inflection points, I got to take my second derivative. So I'll start off with my first derivative. So my first derivative was 4x to the exponent 3 minus 6x to the exponent 2. My second derivative is going to be 12x squared minus 12x. And once again, I'm going to factor out something if I can. I think I can factor out 12x. I'm going to left x with minus 1. And what we're going to do is we're going to say that f double prime of x is equal to 0 when 0 is equal to 12x, x minus 1, which gives me x is equal to 0 and x is equal to 1. So we have a little bit of a problem here, right? We have our first derivative set to 0, x equal to 0, and the same thing happening with second derivative, we get the same value. So I'll just highlight that. So we have to consider then that most likely the x equals 0 is going to be not only an x-intercept, but an x-intercept and an inflection point. So we're going to write that down. So this is going to be x-intercept and an IP, which is inflection point of 0, 0. And this one here is just basically an IP at 1. And if I plug into my calculator, I get a 1. All right. So we got to fill up the chart. So the first critical number that we have to look at is going to be at x equals 0. So I'll always leave a space. So there's my x equals 0. And my second one is going to be x equals 1. So that means that's going to be x is greater than 1. That's going to be x is less than 1 but greater than 0. And the last one is x is less than 0. And here we go. If I were to plug in a value to my second derivative that's less than 0, what's going to happen is I'm going to get a value greater than 0. So if I go back to 12x, x minus 1, plug in, let's say, for example, negative 1, I get a negative times another negative gives me a positive, which means greater than 0. So what that is telling me is that this is concave up. Or if you want, it'll look something like this. At x equals 0, we know that this is going to be 0, and we know that this is an inflection point. And the inflection point is going to be probably something like this. Try to do something better, huh? Close enough. And the next one, we're going to choose a value between 0 and 1 to put into our double derivative, let's say 0.5. So we're going to have 6, which is a positive number, times negative 0.5. It's going to be a negative number, so it's going to be less than 0. So it tells me this is going to be concave down. So concave down will be something like this. X equals 1, we know it's an inflection point again. And it'll be something like this. And the last one, if I plug in a value greater than 1, it's going to be a positive, so it's going to be greater than 0. So it's going to be concave up, which will look something like this. Now you guys are going, what? That doesn't make any sense. So how about I go back and I say, well, if you think about it, we're starting the graph off. So we need something from an end property to a point. So there's my end property to a critical point. So my critical point now is right there, right? So this would be the part that's going up. And then if we see the next part, we say it's concave down, we need the second half. So we know it's coming down to a critical point and coming down. So that makes sense. And then if you think about it, this is the part that's coming down from the previous part. And then it's an inflection point, so it's going to change direction. So it's going to start going up. So that means that it's going to actually be that part there of the function. Let's try and draw a little sketch of this. I can try and squeeze it in that little part there, or I can just put it down below. I think I put it down below. So I'm just going to draw a little sketch. So this sketch is going to go, it's supposed to go over there, and I'm going to freehand it. So we know that we have a point here, an inflection point, which is 0, 0. And it's also probably a critical point. So it's a critical point, which happens to be an inflection point. We know we have an x-intercept somewhere over here, which is 2 and 0. We know, just adding some more stuff to the graph, trying to keep a reasonable scale. And we know that at 1, if I plug in 1, we get negative 1. So 1, negative 1 is right over here. And the other point that we didn't calculate was the x equals 3 over 2, which is 1.5. 1.5, if we calculate, it's negative 1.6875. So that's about here. So this is going to be my 3 halves. And it's going to be negative 1.6875. That's going to put it as a decimal. And now all we have to do is fit what are yellow highlights in the chart above that you look at. You can see. So we can see for the first part it says concave up. So it's concave up. It's going concave up over there up to our inflection point. It does a change in concavity going down. And it's going to continue to go down and change direction again, and then go back through. So our graph will look something like that. Okay. Example 3 at the bottom says, use the function given example 1 to identify the points of inflection. So if I go back to example 1, it was this part over here. So we can see that A, B, C, and E are points of inflection. And I'll put that as a summary. I lost the page again. Sorry. So, and let's put this in writing. So we have point A, and you'll have to flip back and forth to actually see this. We're going, it has something that looks like this. That's a point of inflection. We have point B, which looks something like, sorry, point B looks something like that. Let's see if I draw it better. Oof. Like that. And we have point C, which looks something like changing direction the other way. We have point was E. Let me double check. Go back. It's point E. And point E looks something like this. Then we have point D, which is not an inflection point. And I'm going to start calling it IP inflection point, or point of inflection. All right. Example 4 says use the sign chart obtained in example 2 to identify the points of inflection for f of x, which is equal to x squared all over x squared plus 1. I'm going to use the same kind of concept that we did in the previous example. So I'm going to first calculate my x-intercepts if possible. So for my x-intercepts, what I want to do is I want to set my y value equal to 0, which looks something like this. And we can see if we cross multiply when I have 0 is equal to x squared, or x is simply equal to 0. And if I plug 0 back in, my point of intercept, my x-intercept point is going to be 0, 0. Excuse me. My next thing I'm going to do is I'm going to find my location of critical points, if any. And the way we do this is by taking its derivative. So our original function was f of x is equal to x squared over x squared plus 1. Our first derivative, lots of ways of calculating derivative, is equal to the derivative of the numerator times the denominator. Subtract the numerator times derivative of the denominator, which is 2x, all over denominator of squared. I can expand and simplify a little bit. So we're going to have 2x cubed plus 2x minus 2x cubed. And that's going to be all over x squared plus 1. I really don't need the denominator anymore because I know it's going to disappear. Those cancel each other out. And we have x prime of x is equal to 2x all over x squared plus 1 all squared. And we know that f prime of x is equal to 0 when we have 0 is equal to 2x. Who cares about the denominator now? And x is equal to 0. So we've seen this before. That was our x-intercept. So this becomes now our critical point, which is 0, 0. Next thing we got to do is we got to find our inflection point. I may have wrote a little bit big, so let's check this out. What I got to do is find my second derivative. Yeah, I wrote a little bit big. So what I'm going to do is I'm going to shrink this all up a little bit. Hopefully that works, and maybe this way as well. Let's try one more time. Sorry, this is, again, live, so things happen. Doesn't want me to go the other way, so hopefully that's enough. So inflection point, we're going to take the second derivative, so f double prime. Excuse me. And it's the derivative of the numerator times the denominator. Subtract the numerator times the derivative of the denominator times 2. And squeeze it in there. And again, it will be denominator all squared. Actually, just put to the power of 4. So it's that squared, so it's exponent 4. And before I do anything, what I'm going to do is I'm going to simplify as much as possible. So we know that this can be canceled down to a 3 by reducing that by 1 and getting rid of that at the very end. We can actually say that f double prime is equal to 2x squared plus 2. And then on the other end, we have 2 times 2 times 2, 2, 4, 8, minus 8 x. I forgot x over here, sorry, at the very end. So minus 8x squared. And that's going to be all over x squared plus 1 cubed. and f double prime of x is equal to negative 6 x squared plus 2 all over x squared plus 1 cubed. And we know that f double prime of x is equal to 0 when 0 is equal to negative 6 x squared plus 2. I could have factored out, let me just factor out just to be a little bit easier. So I'm factoring out a negative 2 from the denominator. So I get 3x squared minus 1. So in this case here, it's going to be 1 is equal to 3x squared, or x is equal to plus or minus the root of 1/3, which is equal to plus or minus root 3 over 3, which x is equal to approximately, just so we can visualize how it look on the graph, plus or minus 0.5774. So if I were to do f of sorry, having some difficulties here, negative root 3 over 3, and I put that in my calculator, I'll get 1/4, or if you want, 0.25. If I were to do f of root 3 over 3, put that in my calculator, I'll also get 1/4, which is 0.25. And we really have to check the end properties as well, right? I'm not going to do in this case here. So we got to put all this stuff on the chart. Put in chart, and we'll take it from there. Okay, so we know that the first inflection point that we're going to be working around is negative 1 root 3, which is the same thing as saying negative root 3 over 3. So the second one is 1 over root 3, which is equal to root 3 over 3. We know that these values are for x that's greater than root 3 over 3. This is going to be for x that is less than negative root 3 over 3. And this is where x is less than root 3 over 3, yet greater than negative root 3 over 3. Following the same principle, and you can verify these numbers as when you have a little time, if I plug in a value that's less than negative root 3 over 3 into the double derivative, I get x to be less than 0, a negative number. So that means it's going to be concave down, which means it's going to look something like that. Right? Now keep in mind we only want the first half, right? For the second one, we know it's an inflection point. I call it IP. So that means if it's going to probably be going down like that. And the next one, it's going to be plugging the value. It just was calculated to make sure it was right. X is greater than 0, so we know it's going to be concave up. So if it's concave up, it's going to be like that. And for the next one, it's going to be an inflection point. That means going from a concave up back to a concave down. And for the last one, we're going to have x is less than 0, and it's going to be concave down. So it's going to be like this. So we can actually see pretty much what our graph is kind of looking like, right? So let's draw a little sketch of this. I'll put it down here. One more thing. We can see that we have a horizontal asymptote, right? And that's going to be y is equal to 1 because the degree of the numerator is equal to the degree of the denominator, so we take the leading coefficients of each. So it's going to be 1 over 1, so it's 1. So we know there's going to be a horizontal asymptote at 1. We also know that there's going to be an inflection point. I'll put some values in here. Takes a moment. All right, we know that there's going to be an inflection point somewhere over here and somewhere over here, where these points are negative root 3 over 3 and 1/4. And this is going to be root 3 over 3 and 1/4. And then the rest, if we follow the graph, we're starting to concave down to that point. We're going to have a critical point of 0. We're going to have another turning point and go back up. So our graph will look something like that. Excuse me. So sometimes we need to do something else. We might have to do a second derivative test to actually make sure that our critical points are actually max or min. So the second derivative test is shown there, and then we'll talk about the first derivative test, I think, in the next example. Use a second derivative test to find the local extrema for the exact same example. So it just makes our life a little bit easier. We know that our second derivative, we ended up as being negative 6x squared plus 2, and that was all over x squared plus 1 cubed. So we're going to check the value at the critical point. So we're going to check values at the critical point, which we said that x was equal to 0. Okay, so excuse me, if I do my second derivative of 0, right, what I get is negative 6 times 0 all squared plus 2 all over 0 squared plus 1 all squared. If I do this and simplify it, what I get is 2 over 1, which is greater than 0. So therefore it says that our point 0, 0, which we calculated above here, which is 0, 0, is going to be a local min. One last example. Again, it's a bigger one. So says use a second derivative test to find the local extrema. If the second derivative test is not conclusive, or if it fails, then use the first derivative test to conclude. All right. So I'm kind of predicting there's probably going to fail because we haven't done some of those yet. So if I do my first derivative, we're going to get something else like this, times 1, so it's not going to change. We know that f prime of x is equal to 0 when we have the 0 is equal to 3 times x minus 1 all squared, or in this case here, x is just equal to 1. If I find where f is equal to 1, we get f1 is equal to 0. Therefore, we identify that 1 and 0 is a critical point. If I do my second derivative, we're going to get 6x minus 1. We know that f double prime of x is equal to 0 when we have 0 is equal to 6x minus 1, or x is equal to 1. So if we can see already that it's going to be the same value, right? But I'll put f double prime of 1 is equal to 6 times 1 minus 1, or f double prime of 1 is equal to 0, which means that we have, since we have 1 and 0 are the same as f double prime of 0, therefore it's inconclusive. Therefore, use first derivative test. So here we go. What I'm going to do is just create a little chart. Don't know what I need. Add more, I guess. Not very straight. We know it's going to be an interval. It's going to be f of x, f prime of x. we know the magic number is x equals 1. We care about what happens when it's greater than 1 and when it's less than 1. When it's less than 1, f of x, if I go back and I put in a value that's less than 1, say 0, it's going to be a negative value. So f, right? So it means it's going to be negative. That means it's going to be increasing. If that's going to be 0 as we calculated, and the same thing. That's going to be greater than, and it's also going to be increasing. Therefore, we can say that 1 and 0 is an inflection point. So to recap, what I did is I know that the value is going to be 1 and 0. If I plug in a value less than 1 into our second derivative, it's going to be a negative. That means the only way that's going to happen if the graph is increasing towards 0. And then the next part, again, it's identifying that I'm starting at 0. We plug in a value greater than 2. F prime is going to be a positive value. When I plug in this x equals 2, that means it's going away from it. So that means the graph will become an inflection point. It will be something like this, which makes sense because that's a cubic. The last one, again, let's take our derivative. We have 4, 3 minus 2x all to exponent 3. Then I got to take the derivative of what's inside times negative 2. If I clean this up, I get negative 8, 3 minus 2x to exponent 3. We know that f prime of x is equal to 0 when we have 0 is equal to negative 8, 3 minus 2x to exponent 3, or f prime of x is equal to 0 at x is equal to 3 over 2. If I calculate the value of 3 over 2, if I plug it in, jumping ahead here. If I plug that in, I'm going to get 0. Therefore, our point's going to be 3 halves and 0. If I do my second derivative, right, what do we have? We're going to have second derivative. So we're going to have negative 24, 3 times 2x all squared times negative 2. Or we're going to have f double prime of x is equal to 48, 3 minus 2x all squared. And same thing, f prime of double prime of x is equal to 0 when x is equal to 3 over 2. F double prime of 3 over 2 is equal to 0, therefore inconclusive. Therefore, use first derivative test. Let's create a little chart. But over here we have a little more space. We have one for the interval, one before the inflection point, one after the inflection point. Our inflection point was x is equal to 3 halves. This is our interval. We have x is greater than 3 halves. We have x is less than 3 halves. F of x and f prime of x. So at x equals 3 halves, we know the point's going to be 0 for both. We have that. So if I were to plug in a value that's less than 3 halves, let's say 2, into the original function, we can see that the value is bigger. If we put the double derivative, it's going to be a positive, meaning that it's going to head downwards. Opposite's going to be true on the other side. If we do our, sorry, I'm just fixing up because it looks messy. If we do a value greater than 3 halves for our first derivative, it's going to be a positive, that means it's going to be increasing away from it. So we can therefore say the value 3 halves and 0, that's horrible, and 0 is a minimum. And again, you can verify those numbers, and that's all for this lesson.